Shall we start? Good afternoon, everybody. So it's about time to include particle interactions into our theory, but let me briefly go through what we did last time. We developed the free power spectrum and factorized the free generating functional. And let me just sketch what this factorization was like. We said that there are common factors, right? It's possible to decompose the free generating functional into standardized factors. These factors are called Ij. Yeah. They are let's do it like that. And they are standardized function of three different arguments. And if I write this function down, it is given by an integral over our function a1. That's one of our standard correlation functions. L1 times a2 plus a2 L1 times our parallel projector times L2, and then a Fourier factor that we had like that. All right, and we discussed several steps last time. For example, that you could subtract -1 from this exponential, which means that you subtract the delta function of argument k from the whole expression, which is irrelevant for us, and so on. And together with this function, we could write the free generating functional as a functional of the shift vector L here, as some normalizing factor, and then let me write it like this. An integral over all auxiliary wave numbers, and there I have to correct something that I did, at least not very convincingly last time. There's a sequence of integrals over internal wave vectors, auxiliary wave vectors that we had to introduce, and then we had a product for k larger than k of these generic factors I, j, k. All right, and we saw last time that k is running from 1 to L minus 1, where L is the number of density operators applied, and j is running from k plus 1 to L. And in the script, I finally changed the number of density operators applied from R to L in order to reduce confusion, at least somehow. All right. And then we needed a rule for the complete set of these wave vectors k, I, j here. And this was where I messed up last time. So let me write down this rule again. There we had to distinguish the case k equals 1 from k larger than 1. And this was LQJ minus some sum of k prime jb plus some sum of k aj prime. And here b is running from 2 to j minus 1, and here A is running from J plus 1 to L. And here is just the auxiliary wave vectors here. Okay, and yeah, I told you last time that, of course, this becomes transparent only once you calculate or once you look at specific examples. So, of course, the simplest example is now L equals 3, because for L equals 2, you do not have any auxiliary wave vectors. So, to give an example for this rule, and in the lecture notes, you find this in a bit more detail. So let's say L equals 3. So then the indices J and K run from, well, K is running from 1 to 2, and J is running from 2 to 3. Right? Okay, so then if I apply this rule, and I would say K2, 1. If I choose J equals 2, K equals 1. If I choose J equals 2, this sum is empty because it would run from 2 to 1. So this term does not appear. This term runs, or this sum then runs from A equals 3 to 3. So that contains exactly one term. And therefore, this is just LQ2 plus an auxiliary wave vector K23 prime. Okay, if I have K31, then J is 3. So therefore, the second sum cannot contribute this time. And if J is 3, then this sum contains exactly one term. And therefore B equals 2. So then we have LQ3 minus K32 prime. Well, and the only remaining wave vector has K equals 2. So that is just the K32 prime itself. All right, and with these terms now, you can factorize the generating functional. And you see there is a single auxiliary wave vector. So this is a single integral now. An integral over an internal wave number, if you wish. And then you have this product here of, in total, 6 terms. All right. This is becoming important later. But keep in mind that once you arrive at a free generating functional, essentially you are done, because then you can reduce everything to a standardized function, right? the same functional contribution in all these terms. You just will have to integrate over a number of wave vectors. Make me suspicious. All right, almost done. Yes. So far, so good. That's what I wanted to say once more. Do you have any questions up to this point? Before I get to finally including some interaction. No? All fine? Okay. Then, because it's the last hour or the last lecture before Christmas, it's time to include interactions. And for that, let me return to one way of writing the particle trajectories, including interactions, and then work our way forward. And the goal is now to write down the generating functional, including interactions, but to try and pull out the interactions in operator form such that generating functional, including interactions, would be some interaction operator applied to the free generating functional. This is the goal. And yeah, we are going to carry this out now. But let me first remind you of our way of writing the particle trajectories that we discussed several weeks ago. So there was a free part with a Green's function of t and 0, which just transports the initial positions of the particles in phase space forward in time. That's the free part. Then we had an interacting part. And this I'm going to write as a time integral. All right, now I could use the same Green's function as there, but this will lead to a more complicated force term. So I take a different, namely our Hamiltonian Green's function, different from the first one. To write the interaction contribution to the particle trajectories in this way. And maybe you remember what these Green's functions were. So the Green's function G was this matrix here for every particle, where t is the Seldovich time that we introduced, right? Our peculiar time coordinate, which is the linear growth factor. This was the Green's function G, and the Green's function GH was this one here, where we had introduced what we called the Hamiltonian propagator. Which had this form, right? M was the effective particle mass, which is increasing with time because the universe is expanding and thereby increasing the mutual particle separation. And what we called this Hamiltonian propagator was just the integral over the inverse of the effective mass. So far, so good. And what was F? F was the force acting on the particles, but in this way, right? So F is one of our expressions for the complete set of particles. So the force is acting on the momentum component of the equations of motion. So I write it in this way here. So what this means is that there is a force changing the momenta of the particles, right? And this force term only appears in the momentum and not in the position part of the phase space coordinates because of Hamilton's equation. P dot is dH dq, and dH dq is the force, so it's only the time derivative of the momentum that's going to be affected, and therefore it appears only down there. All right, that's it. Now I can write the particle trajectories conveniently as a free part and an interacting part. And just for abbreviating things later, I'm going to split the notation in this way. Now these are the complete trajectories. That's the complete solution. The problem is, of course, that we do not know where in space and at what time we would have to evaluate this force term here. So this is a formal solution. And to work it out exactly requires some iterational perturbation scheme. Nonetheless, that's the exact formal solution. Now, I can write the generating functional, including interactions, as this part and an interaction part. And of course, I need to deal with that in some way or another. Now, that's the goal, right? We want to find out how can we possibly pull this expression here that contains all the particle interactions in front of the generating function. That's the key point to find out. But before we do that, let me have a look at how we can phrase this, this force term acting on particle number I. All right, so here's the goal. And what follows are a sequence of steps that lead us to this goal. Okay, so what is the force acting on particle I? First of all, you know the potential acting on created by the particles, because we saw that the potential relative to the Seldovich trajectories that we introduce as the free motion is sourced by the nonlinear density contrast only. And then we can write the force as minus m times gradient phi, where phi is that potential sourced by the nonlinear density contrast, and m is the effective particle mass. All right, force is mass times acceleration. Right? It looks approximately right. Okay, and I wanted to have this expression here instead of the more complicated expression that I would get if I replaced the Hamiltonian Green's function by the Seldovich Green's function, just because the force term satisfies the much simpler equation. But of course, in principle, you could also replace the Hamiltonian Green's function there by the Seldovich Green's function at the expense of a more complicated force term. But let's stick with that, and of course, the price that we have to pay is that we now have two different Green's functions in the integral term and in front. All right, but what is this? The complete potential at position Q contributed by all the particles is what? Well, this is the sum over all particles of the one particle contributions to the potential. So each particle is a point mass. Each point mass carries the standard Newtonian gravitational potential. So this would be sum over all one particle potentials taken at the separation between the position Q and the position Qi for all the particles. Okay, now this is easy. So now let's introduce a step that is used very often in many particle theory. Let us write this as integral over some new spatial variable y of the potential taken at an arbitrary separation Q minus y times the sum of delta distributions y minus Qi from I equals 1 to n. Okay, that's pretty obvious, right? And now you recognize that this is the density at position y. And so you see that, first of all, this potential V of Q is a convolution of the potential with the particle density. All right. This should look more symmetric, right? We would have another density factor in there. So if I now want to know what is the force acting on the particle I caused by this potential here, then I would do the following thing. I would take minus the gradient with respect to Q, not Qi, with respect to Q, of the one particle interacting, the one particle potential. And now I have to pick out that particular coordinate Q where the particle I is sitting. So I integrate over all Q times the delta distribution of Q minus Qi. This may look unnecessarily involved, right? But now you see that this is the density contribution of particle number I, and now I'm getting an almost symmetric expression, which reads integral over these two coordinates Q and Y. And this looks pretty nice, doesn't it? Gradient. Okay. All right, so I think what this means is pretty clear. You calculate the force between any two positions and evaluate these two positions at the locations of the particles, or rather you weigh these two positions with the particle number. All right. This expression is getting much easier in Fourier space, like so many things. Right? If you express these three factors here in Fourier space, you get a rather simple expression here. And first of all, you see you have a convolution here between some vector function, gradient V, and the density. So you know that the Fourier transform is just the product of the two Fourier transforms of the two factors. So taking the Fourier transform or inserting the Fourier transform of this gradient V times the density is going to be an easy thing. Once I have wiped the board. I'm going to write this expression as the convolution of the gradient of V and the density. So I know that the Fourier transform of this is the product of the two Fourier transforms. So this would be I times K times the Fourier transform potential. Right? I times k is just the gradient, or I times k represents the gradient in Fourier space. And now you have rho times k. And of course, you need to transform this back. So this is this expression here. Okay. And now I'm going to insert this expression, which represents the convolution, so the integral over y of gradient v q minus y times rho of y by the Fourier transform. And I also will express the density, sorry, also will express the density by its Fourier transform. So this means that the force on particle I, which is the negative gradient of the potential at position I, this is given by minus integral over q, integral over the Fourier transform of the density contribution of particle I, taken at some new wave vector k prime, e to the I k prime times q. So this expression here is just rho I of q. Right? The Fourier representation of the first density factor here. Now I insert the Fourier representation of the rest of the convolution. So this is going to be integral ik v tilde of k rho tilde of k e to the I k times q. And now you see the q integration has exactly only these phase factors left. So the result of integrating over q is going to be a delta distribution in k plus k prime. So then we can carry out the k prime integral, and this will replace this k prime here just by minus k. And therefore you see that this is the integral of should have put the k integral out, but nonetheless, it's the integral over k rho tilde of minus k ik times v tilde of k times rho tilde of k. So where we had two integrals in real space, we have just one k-space integral left if we represent all these factors by their Fourier components. And the goal that I'm pursuing here is that now I want to take steps that allow me to replace the density contributions here by density operators. That's the goal. All right, but for now, you just see that we can represent the force term like that. Okay. So now I have a representation for the force term. Now I can return to the interacting part of the trajectory. So now comes the decisive step, how to move the interacting part out of the integral. Remember, if you have a derivative in an exponential, it's going to create a shift in the function that this operator derivative in the exponential is applied to. So I want to pursue the following thing. I want to have well, let me first of all write the particle trajectories as functionals of a new source field K, whatever K means, right? Keine Ahnung or something like that, or Kraft, or whatever it is. So that's the well-known free part. We don't need to care about that. But now I'm going to replace the interaction term by this so far unknown source field K. So now I get an interacting part of the trajectory that is itself a functional of K. In other words, now I can write a generating functional of two fields, J and K, which looks like this. So this is the free part, I scalar product of J with x0, and then plus I scalar product of J with x bar interacting of K. In other words, I want to drive the particle trajectories with a force that I do not specify. Right? This field K now takes the role of the force term, but I do not specify it in any way. I only introduce the K field here such that I can take functional derivatives with respect to K. Because I now want to apply to this generating function here an exponential operator containing a functional derivative with respect to K, such that I know that the effect of applying this operator will be a shift in K. I will replace the K by K plus something else. Then I will set K to 0, and I will have replaced the K by the term that I want. Very similar to what we had by applying density operators to set of J. We had functional derivatives in the exponential of the density operators, which created a shift in J plus L. Then we set J to 0. We had replaced J by L. Now we're going to play the exact same trick on the interacting part in the following way. Suppose we have an operator which looks like that. Like this, right? I take the exponential of an integral over functional derivative with respect to K times the force term that I actually want. Now, if you apply this exponential operator to a set of J and K, and you then set K to 0 after you have applied this exponential operator, then what it will do will be, first of all, it will replace the K here by an integral over, no, we'll replace the K here by K plus F. And you will set K to 0. And then what remains will be an integral then over T1 of the Green's function times F for T1. That is GH, I'm sorry, that's GH. Thank you. All right, that's what we need to do. And this will replace the K by the F, and this will allow me to pull F out of the generating function. All right. If you don't trust me, arguing with the shift, write this exponential operator as a Taylor series, apply all these functional derivatives in the the order needed, and you will see that it does what I promised. All right. So we can write down what we mean by this, but then of course we will have to replace the f here by the f that is now long gone, right? The actual force term that we need. Now, what was that like? The f was 0 fi ei, and the fi we just calculated, right? We said we can write fi as minus I integral over k times v tilde of k, rho I of minus k, rho j of k. Now we have to sum over all j. I know I wrote this differently before, right? I had just density rho here, but density rho is the sum over the one particle density contributions rho j. Now, if I sum over all of these j, I of course need to exclude I equals j to include the particle, or to exclude the particle I acting with it on itself. This was the result we had before. This is the expression for the force term that we had before. This is where I now want to insert this. But of course, if I want to pull the whole expression out of the integral, then I will have to replace these densities by density operators as well. So what's going to happen is that these density operators will act on the J source field. This operator here will act on the K source field. The action of the K derivative is to replace the K by the F. The F contains the rho hat operators, and the rho hat operators pull down the density contributions from the phase factor of the generating function. All right, are you with me? Good. Mm-hmm. I was too lazy to write this down. Yes, thank you very much. You're right. You're right. So this means that we can now directly convert what I wrote down to an interaction operator that we can then apply to the generating functional, now taken as the generating function of the two source fields, J and K. Okay. So let me write this exponential prefactor in the form exponential of I times Si. The imaginary unit there is more or less convention. With this expression, I mean the operator form of this exponential here. So this means that I can directly specify what Si should be. Now, Si should be a time integral. Now, I need to evaluate the scalar product here of this force term here with the functional derivative with respect to the K field. Now, of course, I need to take the functional derivative with respect to all the components of the K field. But since the force term only has a P contribution, a momentum contribution, this will boil down to a functional derivative with respect to the momentum components of K for each particle I times the force term acting on particle I. This is just the decomposition of that scalar product. So I write this as functional derivative with respect to K Pi of T1 times the force acting on particle I. And the force acting on particle I is this one. And I want to pull out this factor I because I want to write this exponential prefactor here as exponential of I as I. So what remains is this minus sign here. Then sum over all j different from I. An integral over k times v tilde of k, rho I of minus k times rho j of plus k, where the densities are now operated. I see it fits quite nicely together. This will be the functional derivative with respect to a three-component field. This will return a three-component field. This is going to be scalar multiplied with a vector k. So the whole expression, bless you, the whole expression is going to be a scalar. All right, now let me change the integration variable here to k1, indicating that there will be more, and introduce the following piece of notation, which before I write down, I should say to my excuse, this is quite common in statistical physics, right? You integrate over d1, d2, d3, d4, meaning the positions of particles 1, 2, 3, 4. But now we have positions in Fourier space, right? So what this means is an integral over the wave vector k1 and an integral over time t1. It's just a shorthand notation for this double integral here over positions in Fourier space and positions in time. So with this, okay, and if I write -1 as an argument of a function, I mean that the function is to be taken at t1 and minus k1. Same for plus. So 1 abbreviates the position in Fourier space and an instant of time. And this, with this piece of notation, and really this is as awkward as it may look, right? Standard in statistical physics. Then you can write this operator as minus integral d1 k1 times delta k p I d1 now times density operator rho I of -1. Potential Fourier transformed at 1, rho j operator at 1. Okay, and we have to sum over all j different from I. All right, and now we do have an operator that can act on the generating functional as a function of j and k. And we can express our particle interactions by this operator. Now, before I do that, this expression here including the density is often called the response field, because it tells you there's a gradient here, a gradient of the density. It tells you how the particle configuration reacts to changes in the source field K, which represents the force acting on the particle. So the response field shows you how the particle distribution reacts to changes in the particle configuration itself. Okay, now I want to write this as a response field of minus K, and therefore I'm going to swallow the minus sign and the minus K1 here. Then I call this response field of minus 1. Okay? Now, then I can write the whole interaction operator as an integral over d1, response field at minus 1, potential at 1, density at 1 of particle j, which is an operator here. All right, and then of course we need to work out what this response field operator does to the generating function and so on, blah 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 blah. But this is the form of the interaction operator that we are going to apply. All right. So far so good now. Yeah. No, because here it is multiplied with rho I, and this is a sum over all I here. But I stumbled about this across the same thing here. Okay, so let me summarize what happened so far. So what happened so far is the following thing. We set up a generating functional now as a function of two source fields j and k. And we saw that we can include particle interactions by letting an interaction operator, yeah. Yeah, you can do that. No. Okay, yeah. You see, there is a sum over I. So essentially, this is a double sum here over all I and j different from I. if you take care not to sum over a particle, over an individual particle in the interaction term, you can just write integral d1 response field times potential times density. Okay, so that is the interaction operator applied to a free generating function. It's not really free because the source field K is in the particle's trajectories, but let me nonetheless write this in this way. And then set 0 of J and K is this expression here. So far, so good. And the interaction operator, as we saw before, and now let me gloss over the point that we need to exclude self-interaction. All right. Now, of course, applying this exactly is horribly complicated. But we introduced Seldovich trajectories because we saw that the gravitational potential acting relative to these Seldovich trajectories is minimum. Right? The potential is only sourced by a nonlinear density contrast. So initially, it's even 0. And this means that it will be promising to try a perturbative ansatz here. And take this exponential here and expand it into a series. And then we automatically get 0th, 1st, 2nd, and so forth order contributions in the interactions to the generating function. Yes. I think so. I think so, but I don't really know. We still have time. The break. We still have time today. I wanted to show you a result that I don't really know how to make sense of, but it also looks very interesting. Nonetheless, let's have a break, okay? But before the break, here's the program for perturbation theory, right? You say this is 1 plus I times Si minus a half Si operator squared, and so on, right? You expand the exponential interacting operator into series, and you get a systematic scheme for perturbation theory. And like in quantum field theory, this gives rise to Feynman diagram, right? This is clear, right? This gives you the free power spectrum. This is a 3-level. This contains a convolution, is therefore 1 loop level, and so on and so forth. Right? Yes. I have no idea. I have no idea. We don't know that. We just know that if you go to large wave numbers, second order is smaller than first order, third order is smaller than second order, and so forth. We do not know whether this is an asymptotic convergence or a strict convergence or anything like that. Yeah, I'm not really sure this is true. If you have a proof, I would be grateful. Reminds of the old joke, right? two mathematicians talk about Arnold Sommerfeld, the famous theoretical physicist, and of course they complain about convergence criteria usually assumed, not applied, but assumed by theoretical physicists. And one mathematician says, well, usually for physicists, a series converges when the second term is smaller than the first. And the other one says, well, for Sommerfeld, the series converges when the first term is shrinking. All right, have a good break. In 5 minutes, we are going to continue. Kannst du mir dein Argument nochmal sagen, bitte?
Kann ich was?
Kannst du mir dein Argument nochmal sagen, bitte?
Ach so, also in QFT, wenn wir einfach die haben, all das machen müssen, wie das, was wir hier aufgeschrieben haben. Wir entwickeln einfach die Funktionen in solchen Reihen, dann ist das ja einfach ein formeller Ausdruck, das heißt, es muss dann nicht konvergieren für irgendeine tatsächliche reelle Zahl, sondern es ist mehr so eine Art von Buchhaltung über Koeffizienten. Genau, und diese Koeffizienten kannst du aber assoziieren zu tatsächlich konvergenten Reihen über die Fourier-Resonanz. Und das ist sozusagen der Anteil, aus welchem genauen Kontext so eine Reihe, also eine Sammlung von Koeffizienten, die wir auf eine bestimmte Art manipulieren können, eingebettet ist in Funktionen. Und also ich weiß es natürlich auch nicht genau, aber es hat, glaube ich, normalerweise nicht mal so unbedingt viel mit Quanten zu tun, also dann mit besonderen Bedingungen, sondern einfach mit formellen Reihen und wie man formellen Reihen einbedeutet. Also man kommt sehr einfach an den Punkt, dass man du zeigst ja quasi, gibt es zu jeder Sammlung von Koeffizienten eine wohldefinierte Funktion, sodass das deren Taylor-Reihe ist, zum Beispiel. Ja. Und das würde man dann über diese Argumente fahren.
Okay, kannst du mir da was schicken?
Ich kann mal gucken, zum Beispiel das Manfred, sag nicht Manfred eigentlich, Professor sein Professor,
ich weiß, wen du meinst.
Ja, für die Renormierungsrolle. Ich habe dann noch was reingeguckt, aber
okay. Noch ein guter Tipp.
Ja, die Vorlesung.
Die Renovierungsvorlesung.
Ja. Ich glaube aber, es kann auch sein, dass wir noch ein bisschen darauf warten müssen, weil wir erst jetzt zu diesem Zeitpunkt.
Okay, gut. Aber
ich weiß schon ungefähr bei den Abschnitten von was mein Guru aus seiner Lateinvorlesung ist. Das hat ein bisschen.
Okay.
Und vielleicht Ich schreibe mir das einfach mal auf.
Ja, danke dir. All right. Shall we move on? Hannes, Fabio, sit, shut up. All right. Now let me briefly say some words about how to apply this. So we saw that we have an interaction operator that we can expand in this way. Now let's have a look at what happens if we look at the first order in the interactions. That is, we look at an application of the interaction operator directly to the generating function. All right, so I want to look at an expression like that. Now that would restore the interactions in the generating functional, but this is typically not what I want to know. Now, what I want to know is what effect do interactions have on, let's say, a power spectrum or a 3-point function or whatever. So usually I need to apply a sequence of density operators in addition to the interaction operator. So something like this should happen. I have let me call it like this here. Never mind. Up to some number, right? So these are typical terms that we now have if you want to have first order corrections to a power spectrum. If you wanted to have second order corrections to a power spectrum, the interaction operator would be squared, and so on and so forth. But what you see now is that now you have a number of density operators here and two more, because the interaction operator itself contains two density operators. And then, because the response field here contains a density operator. But then in addition to the density operator that is part of this response field, capital B, there is something more. Now the density, all of these density operators are derivatives with respect to J, the source field J. And what remains in the response operator is a derivative with respect to K. Now both derivatives commute. In other words, I can first apply now a whole litany of density operators to the generating functional, and then apply all the response fields that there may be. So let's suppose I want to have an nth order power spectrum. So n equals 2 would be the ordinary power spectrum, n equals 3 would be the bispectrum, n equals 4 would be the trispectrum, and so on and so forth. So I want to have a power spectrum at nth order. In other words, I would apply n density operators after correcting the generating functional for the interaction. Then I want to have mth order in the interaction. In other words, the interaction operator would appear m times here. Then the total number of density operators applied would be L equals n plus 2m. And then I have a whole sequence of density operators. then I would have a whole sequence of density operators that I can apply to the generating functional. And after that, I can apply the remaining M response field operators. Aha. In order to make this more systematic, let me write the response field operator capital B as K times the functional derivative. Take this in brackets here. Now times the density operator with the same argument. Now I've introduced a new particle index JK to count the particles that contribute to this response field operator. And this I'm now calling a response operator with a small b, which is just what I need in addition to a density operator. So this is to allow me to write the result of doing that to the generating functional in this form here. B hat of some argument applied to Z of L and K. Right? So I have the two density operators contained in the interaction operator. So I have a sequence of n plus 2 density operators. I can apply them directly to the generating functional, which will result in a shift of the J field by L. Then I set J to 0 and I'm done. So the effect of all the density operators is known to you, right? This is the set of L and K. So the only thing that remains is to see what happens if I apply this remaining small b response operator to generating functional of L and K. Right, so I need to do something like this. What index should I give to that? Well, I'm confusing myself by indices. Let me write the argument of the response field operator as K. The particle index corresponding to that as JK. So then I want to see what happens if I apply this to the generating functional, or rather, if I write the generating functional in this way. What happens to this expression here? Okay, let me also specify what L is. The sum over an index S, enumerating all the density operators that I have here. S equals 1 to L of Ks times the result of taking the functional derivative, this phase factor here with respect to J and so on. You've seen that before. Right? here I'm enumerating the particles contributing to the density fluctuation with wave number ks by indices js. So that was L. Now what happens if I apply this operator here to this expression? Well, I have a functional derivative with respect to k, but only with respect to the momentum component of k. This will act on this interacting part here of the trajectory. But first of all, it will bring this whole factor down from the exponential. Then I need to apply the functional derivative to this expression here. So I need to evaluate what is the functional derivative with respect to k, e, jk, taken at time tk, applied to x bar interacting. So this is the integral over the Green's function times the k phi. All right, what is this going to give? It's an integral over dt prime, now gh dt prime. Now I need to take the functional derivative of this whole source field k with respect to its jk component and the momentum contribution to that. So this would be 0, 1 from taking the momentum contribution. But then it would give you delta function of the times. And then it would be applied to particle ejk only, particle jk only. All right. Now, of course, you can directly carry out this time integral, and you can directly multiply this matrix valued Green's function, the vector 0, 1. So this is giving the Hamiltonian propagator small g, 1. Sorry. This will be a delta. No, that's fine. Yes. Okay, so that's going to be the result of this functional derivative with respect to capital K. Now you see that what the response field operator B hat does. It's just that it multiplies this functional derivative here with a K vector. All right. But before we can do this, we need to carry out the scalar product here of L with this functional derivative of the x bar I. So then with this result, I can calculate what is L now times functional derivative of this expression. This is what I have to calculate next. Now, first of all, remember that this scalar product contains a time integral again of this L here depending on T prime. So I would have minus the sum S equals 1 to L Ks times the delta function of T prime minus Ts now, because I have to integrate over L and X as functions of T prime, times 1, 0. That's all the L's. Shouldn't use these brackets here. Now I have to take a scalar product with this result here. So this is going to be GH of T prime and TK, right? Because I have to take this as a function of T prime. Times EJK. All right, now we can easily carry this out, right? You can integrate over T prime. This is going to replace that's true. So let me fix this by saying this. Okay. So this is going to replace the T prime here by Ts. Then I have to multiply this vector by that vector in a scalar fashion. So this just leaves the GH over. So the result is simple. All right, so this is just going to be minus sum over S equals 1 to L Ks GH of Ts and Tk. Here you already see important things. Now times delta Ts. So this is the result of what the response operator P hat does to the generating functional. Now you see nothing in this expression depends on the initial positions of the particles. So this means that if I apply this operator here to this integrand, I'm getting this factor down from the exponential. But this factor does not depend on any of the variables in the integrand measure here, so I can pull it out of the integral. So what remains is a simple response field factor, namely this thing here, times now the generating functional with k equals 0. So in other words, if you apply the small b response operator of k to the generating functional, you get this response factor here. Now you need to apply this with, you need to multiply this with a wave vector that is also contained in the response field, ks times kk. You have the Hamiltonian propagator from Tk to Ts times a Kronecker delta here. This Kronecker delta will collapse the whole sum to a single term. You just don't know to which until you fix the particle indices. And now what remains is a set 0 with L remaining, but with K set to 0. That's the free generating function. And this we factorize. And we factorize this into standard functions, in the standard contributions here. So what this is, we do at least know in principle. And then you see that the interaction just multiplies the whole term by this factor here. And that's what I wanted to show you. All right. Yeah. Huh? Mm-hmm. Then you would apply S squared. S squared would contain 4 density operators itself. So for a 2-point spectrum, you would then have 6 operators, 6 density operators to apply. So L would have 6 components. And then you would have 2 response fields to multiply. And the first one would give you a factor like this. The second one would give you a factor like this. You just multiply response field factors to that. Okay, so this is what I wanted to show you today. What have we done? Right? We started from a. What have we done? we started from a free generating functional. We had a look at what is the force between particles looking like. And then we took a lot of care to pull the complete force term out of the integral by converting it to an operator. And the essential trick was to say that if you have a functional derivative or a derivative in an exponential, this derivative is going to shift the argument of the function. So we defined an exponential operator containing the interaction. This allowed us to pull the interaction term out of the integral, but then we had to replace the densities appearing in the interaction term by density operator. And this way we gained an interaction operator. By definition, this is exponential. This means that we can expand it into a power series and thereby get a systematic access to perturbation theory. And what happens in first order we saw, and then this response field operator small b here, that what remains after you have taken the density operator into account, just boils down to having a response prefactor here. And how we handle this, right, in specific examples, we are going to do after Christmas. Right? I wanted to go with you through several examples, how you can then apply or how you can then begin with perturbation theory. At the example of a 2-point spectrum. And then you will see that, of course, as always in this kind of perturbation theory, diagrammatic language is preferred. So I will show you how you can then construct diagrams. You know all that, of course, very well. You can then construct diagrams, and from these diagrams, read off what happens. And then write down terms. And then, of course, you realize that a computer can do this right as well. And then you write some code that develops the complete series of, or the complete sequence of perturbation terms and evaluates these for you after Christmas. I wanted to show you one brief thing where I really don't know whether this is useful or not. Right? But let me briefly show you the following. It still has to do with taking particle interactions into account, but before applying operators. All right. I want to begin with the following expression. Force of particle J on particle I. And we had an expression for that. That was returning to function, right? We are still in the integral functions. We saw that, right? It's just a Fourier representation of the force term. And now I'm going to introduce that rho I in Fourier space for wave vector k is just the integral Fourier integral, right? So this is e to the minus I k times qi. And I now want to use the phases because they are the only thing that identify the particles. Right? I want to introduce the phases. I'll call this phi I. If I want to sum over all the j's here, I'm getting this. Now let me use this, Newton's third law, right? No big surprise. To say that this. And now this takes automatically care of throwing away the II part, right? Because I have antisymmetry. So I can write the Fi as minus I. Now, integral over k, k times v tilde of k, that's this factor here. Now I have phi I complex conjugate times phi j minus phi j complex conjugate times phi I. And I need to sum over all j. Okay. So I have the sums over all j over all these phase factors here. Now I can write sum over all j of phi I, phi 1 plus phi 2 plus I'm expressing this as a scalar product, right, of some vector epsilon n times the vector of phases, and epsilon n is a vector that contains ones in all its places and has n dimensions. I can write like this. Now I need to evaluate j times Green's function and so on times 0 Fi, and I need to integrate this over time. But this means that I'll just have to multiply Fi with a component J P I. In a rather sloppy notation, the exact notation is in the script. you can therefore write that this is some integral. Now, some vector A times the complex conjugate of the phases times some vector epsilon n times the phases phi I minus A times phi times epsilon n times phi star. Integrals over that, right? But the integral kernel will contain an expression like that. So I can write this as phi dagger m times phi, and m is a matrix that looks like A tensor epsilon n minus epsilon n tensor A, so that's obviously an antisymmetric matrix. In other words, I can write the complete interaction term as an integral over phi dagger times m times phi, which looks suspiciously like something quantum mechanical. But now the problem starts, and that's the reason why I don't really know whether that is useful or not. I'm going to be done in a minute, so you can escape very quickly. You can escape all the time anyway, but so in other words, I can write this scalar product here as some time integrals, some k integrals of phi dagger m phi, with m this matrix over there. Now, you can apply the spectral theorem and say, well, if you have a matrix like that, which is first of all real, and antisymmetric, then this matrix is normal. In other words, it commutes with its adjoint. So this means that m dagger m equals m dagger, which you can show very quickly from that, is just minus m squared. If this is the case, right, if you have a quadratic form with a normal matrix here, then the spectral theorem tells you that this can be diagonalized. And it can be diagonalized by a unitary matrix. In other words, we know that there exists a unitary matrix U such that U mu dagger equals a diagonal matrix, which of course makes this makes this interaction term very, very simple. And it just decomposes these interaction terms into a sum, and then you can evaluate all of them individually. The problem is that if you have an antisymmetric matrix here, then these eigenvalues here are pairwise opposite. So lambda 2 is minus lambda 1, lambda 4 is minus lambda 3, blah, 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 blah. And what do you do if you have an odd number? There is at least one zero among the eigenvalues. This is bad because this means that if you have an odd number of particles, the determinant is zero anyway. But in any case, this means that you can introduce new variables for the particles. And this somehow reminds me of your question last time, such that psi equals u phi, and then this whole quadratic form here decomposes into this. In other words, I can introduce variables in which the complete interaction term decays into one particle contribution, where I have introduced a new pseudo particle psi by this. Okay, now it turns out that, and you find the recipe in the lecture notes, that in fact it's easy to calculate the eigenvalues of the matrix M. For example, if you want to apply this now to the problem of calculating a power spectrum, it turns out that M has n minus 2 eigenvalues which are all 0. N minus 2 eigenvalues which are all 0. This means that in this case, you have two contributions left in this sum here. In other words, there are two pseudo-particles that contain the complete information about the interaction. You can also calculate the other eigenvalues, plus or minus I times root 2n, if you want to know. Once you have the eigenvalues, you can calculate the eigenvectors, and you know that this unitary matrix here has the eigenvectors as columns. So you calculate all the eigenvectors, and again, you find the recipe in the lecture notes. In other words, you can explicitly calculate, or you can explicitly construct these pseudoparticles. And then I don't know how to go on. So in other words, it is possible to decompose the complete interaction term and factorize it and introduce, if you want to know an nth order correlation function or nth order spectrum, you can decompose this into a sum with n terms. Power spectrum, 2 terms, you're done. And I don't know how to go on. This looks so nice, right? And I don't know what to do with it. Maybe have a look at that and let me know what you think about it. As I said, right, the complete recipe without all this, all these maneuvers here, is in the lecture notes now. Maybe you have some inspiration over Christmas, I don't know. Okay. Thank you for your patience. All of those who I don't see anymore before Christmas, Merry Christmas. Good start for the new year. And then we'll meet again on January 9, 10, 11, 12. January 12th, we're going to be back. I will try to create a nice problem sheet for you to solve until next week. I'm not sure if I succeed. All right. Bye-bye.